I will refer to this. Okay, let's continue. One moment. If we have some, I'm at the university now because I have class before you with students offline. So if you see that my connection is not really good, if we have some lag between voice and explanation, please give me some feedback and we will try to fix this problem. Okay. Let's start a demonstration one more time. Where is it? Okay. Today we will talk about we will have two parts of the lecture: introduction, and after introduction we will talk about linear regression model because we've had practical task about this, but no theoretical information without any theoretical explanation. Yes, so we will explain what is linear regression using theoretical approaches. Hassan, could you turn off your microphone because I hear some.
Yes, yeah, sorry, I'm sorry.
Thank you, thank you. So in the previous lecture, I've tried to start with introduction also to some problem. When you have several objects and we think that they are the same, how could we describe this connection between objects, and how could we describe differences between objects? It's really difficult problem, and it's about multivariate systems analysis issues. Can the analyzed objects be considered identical, and by what features can one explain their possible differences? So in this slide, you may see an ECG signal. Yes, ECG signal reflects electrical activity of the heart, and we see contractions of the muscle. Yes, because our muscle like electricity engine, so electrical engine. So we may measure potentials between some points in our body, and we may use I will show you lids. Yes, it's like a small device which allows you to record ECG signal, really small. You just you're wearing it during the day, and to this wires, you just take electrodes and fix it into your body, and you register your electrical heart activity. Yes, during the day, it's about 24 hours or more. If you need to detect some random situations, for example, you may just have some heartache sometimes, so you need to fix ECG signal during your heart attack, so you need to wear this device not one day but weeks and months. Of course, it's impossible to analyze this signal manually because it's a lot of information, and we need to detect some algorithm, automatic algorithm, which do something like a doctor. Yes, analyze the signal and make some decision give you some decision about your health state, yes, or about heart. In the case of heart, we have standard complex QRS complex, which express one contraction of the heart. Yes, it will be here. Do you see my cursor or not?
See what?
Cursor.
No. Yes,
No.
yes.
Okay. Yes.
But maybe you
I will try to use laser like this. It will be better.
Yes.
So this is one contraction of the heart muscle. Yes, we see that in the first one and the second one really close to each other, but of course there are varies in some range, and we need to construct some model, some number of features which express this identically or do we have identical complexes or not, or someone else. In the slide we see two examples of extrasystolic complex. It's some abnormal contraction of the heart. You see that we have two types of this pathological contraction. But for us, they are the same actually, because it's really difficult to see differences between these two extrasystoles. But actually, yeah, there are different, and we have this part. You see that it's flat, flatter than here. Let's see some messages. Awesome. Okay, so we need Benedict. Are you talking? I don't see. Yes, doing better. So we need to analyze what our doctors think about, how to analyze differences, what should we look at to differentiate our objects. But for extrasystolic complex, we see that distance between our object and the previous one less than in normal case. So we may explain that if you have short interval between two objects, it will be we may predict that it's some extrasystolic complex, and we see that after this complex we have some pause, yes, and also like a predictor. I will upload this lecture to our classroom, and here you see a link where you may find information about some biological processes in the heart. They will be, I think that this video will be useful for you if you are not familiar with the heart activity and something like this. So you will find information about extrasystolic nature. So the question is, how could we explain properties of our objects in order to find identical objects and different ones? The second question is, how could we group our objects? In this slide, you may see a screenshot of program for records analysis, records from Holter monitor. So this is 1 day of ECG signal. See here, you see trend of heart rate, value heart rate. You know, I hope that this is number of heart beatings per minute. It's like a dynamic plot. Here you see a small part of the signal in two leads. We have synchronized records in several leads from 3 to 12 or more if you need to analyze heart closely. So and in the this part you see groups of complexes. These groups were generated automatically, and in some sense, in one group we have complexes which are identical. So algorithm calculates some distance in some way between complexes and grouped them into clusters. These clusters, you see that we have some normal complex, abnormal complexes, this first one, second, and the third. And here we also have some strange shape. And we have some noisy groups, yes? So why should we do it? Why should we combine objects in groups? It's only for doctors, because nowadays we could not perform diagnostic conclusion without doctor. So we need to show everything we've count, everything we've calculate, and ask, is it correct or not? So the doctor says, yes, it's correct. Okay. And of course, it can be wrong. We may automatic auto algorithms has some errors. It's okay, and doctor will see some errors and change results of automatical detection. In this case, we need to prepare some tool to show everything in one page. Yes, here we have about half a million of complexes. It's normal, and of course it's impossible to go through the through all of them. So we just combine it in clusters and show doctor, and doctor click to this cluster and run through these complexes. And you will see that in this trend, you also have distribution of these yellow bars. It's distribution of these complexes type of this type during the records. So it's really important to prepare good visualization for analysis, because without this visualization, it's impossible to prepare some decision about health state. So how could we group these objects? It's also a good question, because we may compare these complexes using signals, so counts, yes, digits of time series. We may use some parameters. We may goes from signal to parametric description, and also it's we need to design some algorithm to perform it. The next question is the spatial or temporal variability of the desired described objects, and what are its spectral properties, structural properties. Unfortunately, our parameters varies during the time. They are connected with our activity, with alcohol, drugs, and so on. So when we define some model, we need to include in this model some variability. Yes. And if our parameters has a constant mean value or standard deviation, so it varies in some range, is great, and we should take it into account. If not, also we should take it into account. Oh, sorry, Russian Russian title. Changes. Changes in what properties leads to systematic causal changes in others? It's also a good question, because when we analyze our objects, which integrated in some complex system. It means that we have several connections between heart and breath, for example, yes. And we also need to remember that we have some trend of heart rate. This trend connected with the breathing, for example. And how could we predict the state of behavior of the analyzed object? That's also a good question. When I have new patients in our hospital, it's great if you understand how long this patient will be here. So we may predict how many, I don't know, drugs, how much money we will spend on this one patient if he has some specific disease. It's also a prediction. It helps us to plan our budget. If you will think about all these questions, we will go to data mining approach. During these days, we have a huge amount of data, and we want to analyze, and we understand that this data is really interesting. If we will deal with it, he will try to find some dependencies in data. So data mining, this is a technology that is designed to search large amount of data for non-obvious, objective, and useful in practice patterns. For example, we may analyze some, I don't know, which items customers buy in my market. I may analyze these items and we'll find some connection. For example, it was some fun research when data scientists find connection between customers which buy beer and Pampers, Huggies for babies. Yeah, Pampers, it will be in English, yes. Pampers. Yeah. Okay. So that's beer and Pampers goes together. So they just take and they start sell it together near one by another, and it increase average bill for the customer. So it's really interesting. We will try some, but it's really important that we are trying to find some useful patterns, not some interesting, but useful for practice. Data mining really close to physical experiments. We have some hypotheses, several hypotheses, and we try to analyze them. When we collect experimental data, we organize our data, in particular in form of tables. The most popular form, it will be our database, yes. And we start to search for such methods of processing that would make it possible to discover new knowledge about the analyzed process in the initial data. So this is our standard data mining steps. We make some experiments, collect and organize our data. Sometimes it's really not very easy, because if you have I don't know, bank system and you want to find dependencies between some features, you need to take these data from different sources. Yes, if you have different sources, you need to find some person who deal with this source, and using some SQL requests or just copy paste Excel tables, you may collect these data sets. It's also about data engineering, because there are several professions which are grouped in data mining story. but we will talk about it later, not now. So at the same time, this knowledge about dependencies between inside the data is always for any complex phenomenon remains to some extent approximate. The deeper a real complex system is analyzed, if we have human in our case, when we are talking about biomedical engineering, the less definite our judgments about its behavior become. So we could not predict anything if our system is really complex. I think that it's an intuitive conclusion. And also some sedation. The research is constantly between the scale of complexity and the horribleness of unreliability. On the one hand, the model he built must be simple in mathematical terms so that it can be investigated with the available tools. On the other hand, as a result of all these simplifications, it should not lose the rational kernel of the essence of the problem. So we should use simple model, but not too simple, yes? And we try to find a balance between these approaches. And also some problems. We have some fundamental plurality of models. We don't know exactly what parameter determine our process. So it's extremely important to have some list of hypotheses, and we just compare the results of interpretation. We could not, in a scientific approach, you should check your hypothesis and make some conclusion about this. The result of statistical analysis is then no longer some indisputable truth, but useful, in some case optimal, yes, models of the phenomenon under study, which can be compared with each other and later defined, supplemented, or replaced with better one. It's a really, it's always a process. You try something new, sometimes, and in some moment you just say, stop, I will deal with this model. It's enough for me, and okay. But you need to understand that it's not the better case. It's optimal for your task maybe, but not the best. To explain and predict the structure or behavior of a complex system, it's possible to build several models that have the same right to exist. This is our rule. And careful diagnostics and extensive verification of the considered models are important. Don't forget about it in your work. So, and really our gold rule for models: garbage in, garbage out. It doesn't matter how good is your model, but it extremely matters how good is your input data. So some joke here, yes, this is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Just stir the pile until they start looking right. You just playing with your data, trying several stuff, and you will see accuracy, for example, 80%, and you say, okay, that's good, but actually not. If you have garbage in the inputs, it will be not correct. You need to analyze what are you doing. Yes. And we are going to machine learning concept. Machine learning, it's a part of mining, of data mining process. It's some conglomerate of algorithms and approaches, and we have some basic ideas. And this is case-based reasoning. So we have some previous collected examples. We use model-based reasoning, so we create some models about this data, And the main requirement is availability of training information. So we need training information from real experience. And as a rule, this is a sample precedents, situational examples from the past of a known outcome. So we may collect information about our patients for the last 2 years, for example, and trying to fit our model on these patients using these precedents. So in the general aim of the machine learning is to construct an algorithm to generate observations of past observations or situations for processing new, not previously encountered cases, the outcome of which is unknown. So we need to predict something actually, yes, using our experience. And there are several machine learning tasks. Classification problem, it's when we are trying to find to which class new object belongs to. And we know that we have, for example, patient with diabetes, we have new patient with some parameters of this patient, and we try to classify that this patient has diabetes or not. We have regression problem. We're trying to predict unknown values of response with known predictor, and we did it in our practice last time. Yes, it was a regression problem. We're trying to predict, I don't know, we may predict level, I don't know, sugar in the blood using information about food and diet and level of insulin in the blood, something like this. Clustering problem, it's about unsupervised learning when we don't know class labels, but we want to divide our data set into several groups using objects. So this is unsupervised learning. We don't know right identify close object in our picture face. The same, the most popular. Forecasting problem, we also trying to predict something to forecast, but it's close to a time series analysis. For example, I see some messages for a moment. And knowledge extraction task, when we try to extract some information from the text, for example, we may analyze tweets with some tag hashtag, for example, with Trump, and we will try to analyze is we have negative or positive reaction to this hashtag, for example. Yes, else it will be knowledge extraction, because using this information we may make some decision and some action on this decision. If you have negative reaction to some situation, we may try to prepare some good news to change the situation. And the main problem which we have in machine learning in our sphere is small volume of training sample. It's really difficult to find a lot of patients with cancer. It's good, of course, because we don't want to have a lot of patients with cancer, but we want to construct some method which allows us to detect cancer but we couldn't because we had no data. We have no enough data. Incorrect input data. It's also a problem because you collect data manually. It means that some doctor just prints results of some results of laboratory tests manually, information about patients, and you will have missed data, you will have wrong data, outliers, and you need to clear your data. And the third problem goes from the first, overfitting. If you have small data set and you are trying to train your model, you train your model on these I don't know, 100 of patients, it means that this model will see not general dependencies in data, but this model will see only this case of 100 patients. For model, it's you need to I don't know, 500 patients, for example. Yes, overfitting, we'll talk about it later. It's a really big problem. You could not create general model, but it's your aim actually. So it's something introduction to data mining tasks, some problems in object analysis, and in our classes we will work with objects in multidimensional feature space. When we try to describe patient using information about his disease, age, I don't know, sugar level, heart rate, and weight, height, and so on. So some number of parameters. What is feature? Feature is some parameter of the object which meaningful for analysis. We will talk about feature engineering and feature selection a little bit later, but we have object as a point in a data space. And we will start with linear regression, like a really important method to analyze dependencies in our data. And this method has several applications, but in the beginning, we need to define what is it. We are using linear regression when we want to find linear relationship between target and one or more predictors. What is target? In our case, it's income. In this example, we have 3D plot. Yes, we have years of education, seniority, and we are trying to predict income using these two parameters. We have several observations. It's our examples, it's our experimental cases, yes, and we construct a plane here which describes the general relationship between these two predictors and target. There are also some additional name for these variables. It's independent variable and dependent variable. So predictor and target. And there are two types of linear regression. Simple linear regression if you have one predictor and one target, and multiple linear regression when you have more than one predictor. We will talk about simple linear regression when we have only one predictor. It's really useful for finding relationship between two continuous variables, and one predictor is x, or independent variable, and other is response y, or dependent variable. So it looks for statistical relationship between x and y, but not deterministic relationship. And this is our model, actually. We have some linear components, which consists, which described by linear equation, b0 plus b1 multiplied by x. So this is standard linear relationship line, yes. And we have some random deviation from this linear relationship, random error. And combination of these two components gives us our dependent variable or our response. This is model of linear regression. Just, fix it in your mind. How could we analyze? How could actually our aim to construct line which gives us the best prediction for our experimental cases. We have real value of salary. In this case, it will be I. And we have predicted, you see this green cross, it is our predicted value of Y with this sign. How could you just help me? How could I call this upper triangle?
It's in French, chapeau, which means hat.
Hat, okay, it will be Y with hat, okay?
Why would you do French? Should be in English.
It will be Y with hat in our classes, okay? So it's our predicted value using linear regression model. And you see that these lines is residuals, actually. Residual is difference between prediction and real value of object, of our target. They are not perpendicular to the line. So it's not a distance, because if we have a distance, when we try to find a distance, we need to calculate distance to line using perpendicular vector, yes? It will be distance. But in case of a residual, in case of error of prediction, it will be this vertical line, okay? Don't miss this, please. So we need to find coefficients b0 and b1, which express this line, and in some case gives us the better results of prediction. How could we do this? We need to minimize error of prediction, and this error will be square of errors for all observations. So we calculate the sum of deviation from the regression line, but take it in square, because we should be sure that all our errors will be positive. And also we will need to give more attention to outliers, values which are far away from our regression line will give us more powerful error to the estimation. So we just take square here. This is our optimization rule, yes? Also, please understand it. So we will try to find B0 and B1, which gives us minimum error. And some information about this in these slides, text information. So error is the distance between the point to the regression line, not the distance difference, actually. Prediction and real is square. Total error should be minimum. If you want, you may just trying to find these equations from this formula, because minimum it's like an extremum of the function, and function extremum should be equal to 0, yes, it means it helps you to find this extreme point. And the total error will be minimum if B0 and B1 are calculated as follows. So you may use these equations in order to calculate regression coefficients for your
Sorry,
regression.
one question, please.
Yeah.
It's been a while since I've had my statistics classes. On the total error function, not function, equation. Yeah. Why don't we include the error parameter?
Because our error is equal to our real value y minus predicted value of response.
Oh yeah, it's just an equation, and yeah, okay, sorry, never mind.
So they are the same, but here you have several interpretation of the same idea. Our error is equal to prediction minus real, or real minus prediction. It doesn't matter because my sign will be a plus anyway. So we just calculate sum of errors, and we will try to find the minimum total error. And
sorry. In that practical task that we upload to the class, Google class, to find the coefficient 0 and 1, we use this formula.
Yes, you will use these formulas in our practical task. Yes, you will take these formulas and just repeat them in MATLAB.
Okay.
This sign, this line means mean value of y, yes, and also here the same for x. It's mean value of your variable. It's standard equations for linear regression model. What about analysis? Of course, sometimes we just need to predict some unknown values for a response. Yes, as here, we may predict salary using a known experience for our new colleague. Yes, we may just calculate salary using this model, but it's not only one application of linear regression. We may also look at our coefficients B0 and B1, and we may try to analyze what we have in our dependence. If B1 are greater than 0, then predictor and target have a positive relationship. It means that if x increase, y is also increasing. So we'll have increasing line. When B1 less than 0, it means that you have negative relationship between two variables. B0 is also shows out the value of our target for predictor when predictor is equal to 0. It's like a shift. Sometimes your model does not include 0. For example, when you have weight and height, and you're trying to find connection between them. If height is equal to 0, it means that weight is also should be equal to 0, and you may try to think about if is linear regression good for this case or not. But actually B0 is like a shift. Yes, so your salary starts with B0. For new colleague without experience, you may predict normal salary. Yes. There is another way to find coefficients. It doesn't matter. It's also one formula. In several sources, in several books, you may find B0 and B1, theta 0, theta 1, A and B. There are several notations, but you need to read original equations for y, and you will find where b0 it's like a population y intercept, yes, and slope coefficient b1 can be also ab and theta 0, theta 1. Just okay. We may analyze negative or positive relationship it is, or and also we may see value of the if coefficient has for example, you have not one predictor, but you have, for example, 10 predictors. You have 10 predictors in multiple linear regression, so you have 11 coefficients, yes. But you may look into these 10 coefficients for features, and you will see which features more useful because they have more impact to your target, and they will have coefficients that bigger than others. You may sort your features using coefficients, and you will see the most important features which influence to your targets more than others, and you will see some unimportant, unuseful features which has coefficients few value of small amount, yeah, that have coefficients less than previous ones. So you may just run prepare some ranking system to select important features. This is one more application of regression feature selection. When we construct linear regression model, it's really important to verify this model to analyze the results of modeling. In real life, we don't know about dependencies between targets and response. We may just assume that we have linear relationship. To perform the analysis, we need to calculate residuals. So as you remember, our prediction consists of two parts. It's deterministic part and statistic part. So deterministic parts covered by the predictor variable in the model. It's our line, b0 plus b1 multiplied by x. Stochastic part reveals the fact that the expected and observable value is unpredictable. There will always be some information that are missed to cover, and this information can be obtained from the residual information. So what is a residual? A residual is our difference between real value of our response and predicted one. So we just calculate difference between prediction and actual value and plot it in residuals plot. You see that these two dots from here, yes, and these three dots goes to this part of the plot. We just turn it into some angle, and we will obtain our residual plot. How could we analyze if this model would? We have some, it's also an example, doesn't matter, characteristics of residuals. Residuals do not exhibit any pattern, it's random. And nearby residuals should be same, and they indicate that there is some information missed by system. So if you have some correlation between points, it means that we missed something in our model, and we need to return to synthesis of the model and add into our model. So what does it mean that we have some pattern in our residual? We have you see that in the third graph we have quadratic dependence between x and residual. It's our residual, yes. In the second plot, we see that variance of the data set increase with x, yes. And also when we have random distribution of the residuals, we will obtain random picture, and it means that we don't have any problem. So if we have non-random pattern, it means that we just missed a variable which has significant contribution to the model target. Yes, so we need to return to our model and add this variable into model. We may missed some non-linearity, so we may fix this problem using polynomial regression. And also it can be no interaction between terms in the model. It's also real case. So this is our non-random patterns of the residual plot, and it's bad for the model. If we see residuals varies and we may find some pattern here, it means that we've missed something. And I don't see, sorry, I will open also one. I see that this presentation is not new. Sorry, I will open slides where I have more information about residuals. One moment. So what about ideal residuals? They are symmetrically distributed, tending to cluster toward the middle of the plot, and they are clustered around the lower single digits of the y-axis. So they are between close to 1 or 2, yes, because when they have high value, it's not very good. And in general, there is no any pattern, or you could not find this pattern in residuals. We've talked about it before. And also aren't evenly any outlier. You may see in this, where's my laser? You will see that here we have some outlier, yes. And also here we have some pattern, and here we have some changes in variance. And some example of non-ideal residual plots and their diagnosis. Y-axis unbalanced. You see that in this case you have distribution of your residuals which are close to left part of the plot. It's not good. Heteroscedasticity. Heteroscedasticity. Yes, that's correct. Heteroscedasticity, you need to remember this term, because heteroscedasticity, it means that your variance changes through your x-axis. So it means that in the beginning you have small variance, low variance, and this variance increase with x value. Yes, it's bad. Non-linear relationship between residuals and x. It's also about pattern outliers. Large y-axis data points. Here you see that you have these data points that are close to 10. It's really bad. X-axis unbalanced. You see that your data points just clustered the left side, and here you have some outliers. It's bad. It's all about visual analysis of your plot. So you plot your residuals, look at them and think, do I have any problem here or not? There are some metrics to evaluate the efficiency of your model. The most popular R-squared value. This value varies from 0 to 1. If it's close to 1, it means that your predictor perfectly accounts for all the variation in Y. So variation of your response may be described by X value. And if your R-square close to 0, it indicates that predictor accounts for no variation in Y. So if you have small R-square, it means that your model bad. So it doesn't describe connection between X and Y. Also, one metric to estimate efficiency of your model is the regression sum of squares. It's your actually it's your error, or not error. It's how far estimated regression line far away from horizontal line. So when you have no relationship between X and Y, it means that you have horizontal line, because X varies, but Y does not reflect changes in Y X. So you may calculate SSR, distances between mean value and your predictions. Sum squared error, it's your average, it's your total error of prediction. You've seen it before, difference between a real value and predicted. And also SSTO, total sum of squares, tells how much the data points move around the mean. So how far away real value of your target, far away from the mean value. So this variation of data itself without model. So you see that in this case, you don't have model impact to SSTO. And R-square value calculates combination of sum of square error and SSTO. And you need to use this formula in your practical task. And also, it of course connect with the correlation coefficient, because it's correlation coefficient is a square root from R squared. So they are close to each other. Yes, because of course correlation coefficient reflects linear relationship between two data sets. So that's about linear regression. What you should understand, that we have some model which consists of deterministic part and statistic variation near this line, that we may construct our model for any data set, for any X and Y, but we need to analyze efficiency of this model using visual analysis of residuals, and we need to evaluate some metrics. For example, R-square value, yes. And also in your practical task, you will find information about, in your practical task, you will find that you need to calculate correlation between X and residuals. And also you need to prepare Goldfriend quant test, which reflects heteroscedasticity. So if your variance varies through the X, this test will show you that you have different variance on your data set. in your residuals. So you have some additional information about the residuals in your practical task explanation. You may go to these links and also read about it a little bit more. So I'm ready to answer the questions. Do you have any question?
When are you going to provide us with the links? The YouTube video and the rest.
When?
Sorry, when are you going to provide us with the links?
You may find links to reading materials in the task, which was uploaded.
Okay.
I will show one moment.
No, it's fine.
So in reading materials here, and also we have some data set for the research, for the future research that play with that set. And also I will attach its presentation, and here will be link for YouTube where you will find information about heart activity. So that's all.
One more question, like, can you please go back to the ECG?
Mm-hmm.
Okay, so if we have an electromyograph, and let's say that we try to mimic the heartbeat with our hand, with contraction, and could it possibly look like that? Yeah, I think it could, right? Somehow, because it's like it's the same thing, but it's a lot denser with the hand because you contract the muscles for a lot of time.
You see, you have difference between amplitudes. You have different magnitude of the signals. In case of electrical activity, you have millivolts. Yes, it's about 20 millivolts for your QRS complex. For muscle activity, you have higher magnitude of the signal. And this idea the same, yes, you just fix potentials between 2 points. It's really close to myogram. But also in myogram, you may pass electrical signal through your tissues and analyze the response of the muscle. Yes, it's like an active measurement. In case of ECG, it's a passive measurement. But
it's the same principle, yes?
Yeah, actually, yes, yes.
Yeah. Okay.
You may register muscle activity using ECG recorder. So, but when you need to analyze ECG, you need to filter out all muscle artifacts. So muscle activity, it's like a noise in ECG signal, unfortunately.
Thank you.
But I do.
So I have a question.
Mm-hmm.
When we're using linear regression, for example, we want to analyze a data set. What exactly are we looking out for? Are we trying to reduce the error, or we're trying to discover an error? Or basically, what exactly are we looking out for if we want to analyze a data using linear regression or quadratic regression?
So you want to understand the aim of this analysis, yes?
Exactly.
There are several applications. For example, we want to predict response when we have some target value. For example, we want to predict level of the sugar level in the blood when we have some regression model which constructs on base of I don't know, food activity, some I don't know, insulin level, and we use these parameters of the patient, calculate output of the model. We calculate Y value, yes, using our features. And we may predict sugar level and make some conclusion that you need to take this dose of insulin after your dinner, for example, yes. So the first aim to predict some unknown value, yes, of y of our target with some set of predictors. This is the first application. The second application is to analyze dependencies between targets and predictors. We may analyze which feature is important for targets or not, because regression reflects dependencies in the data also. This is the second one. So we just look, in the first case, we are looking for a y variable value, yes. In the second case, we just need to obtain coefficients, and we look into coefficients. That's all.
Sorry. Yes.
It might as well be arrhythmia, right?
Pardon?
It might as well be the recording of possible arrhythmia.
This case?
We can no, in general, I mean, we can also use it in combination with the machine you showed us earlier to, I don't know, monitor arrhythmia.
In regression, when we are talking about arrhythmia, it's some class or event, yes? In regression line, we have quantity values of targets. So our target should be some number, some value. In case of arrhythmia or no arrhythmia, we have classes. It will be not regression task, but it will be classification problem. And we will talk about it later, because in this case we have logistic regression. It's also regression, but logistic, because we have 0 and 1 classes. We may I don't know, may select dose of the drug to our patient using his parameters of weight, I don't know, some model. Regression model consists of set of features and coefficients. Coefficients you calculate using your experimental data, yes? And your experimental data, it's like a table with columns. In columns, you have features. In rows, you have observations. And you just analyze your data set. I will show you an example. Where is it? In Kaggle. It's like a data set which you have here, link you have here. Life expectancy from World Healthcare Organization. And here you will find notebooks with data analysis when you are trying to find dependencies in your features. It's in Python, not in MATLAB, but it doesn't matter. We will try to find some scatter plots. So it's like data analysis. We are looking for dependencies in our not here. I think that not here. Sorry. We see that in the title R-square score is 0.97. So this man construct some model which predicts outcome life expectancy with good R-square score. I wanted some plots. Where is plots? No plots. Nah, I don't like this notebook here. I remember that here will be plots. We may analyze a relationship between data, for example, like here. Yes, we may try to find linear relationship between alcohol and schooling. Yes, and make a conclusion. Do we have any linear connection or not? And also, we may...
Sorry, my question is this, because when I was studying linear regression last week, what I'm trying to understand is, do we use linear regression to reduce the errors or to find the errors or to predict the errors? Or what exactly are we doing when we're using linear regression? Because of course we have RS square, we have standard error of the estimate. So what exactly are we doing? Are we using this linear regression tool to be able to reduce the errors within our data set, or we're using it to find the errors or the relationship? So that's what I really want to understand when we're trying to analyze, because you said we could predict and analyze using the coefficients. So when we're analyzing, are we trying to find the errors, or we're trying to actually reduce the errors?
We don't have errors before model. So we will obtain errors only when we construct some model. Are you talking about this first step? In this first step, we just create some test data set. It's like an example, nothing special. And only here in the second part, we are using least squares methods how to calculate B0 and B1. And we just calculate coefficients. Of course, these coefficients calculates in order to decrease the error, yes, to minimize the error. But it's like an optimization problem. It's not about linear regression aim. I'm a little bit, I don't understand maybe your question in full.
Okay, let me explain it better now. Okay, for example, let's say we have a data set from, let's say we pick, we're trying to analyze the relationship between alcohol and blood, of, for example, alcohol and diabetes in people. And so we get several data from different ages of people in their relationship with how they took alcohol and the presence of diabetes in them. So now if we get all this data set and plot it out, so basically what you're saying is that we can use linear regression to see if there is a pattern or there is a correlation to our hypothesis.
Yes, we may use linear regression to find correlation between them. And we will just take our B0 and B1 equations, calculate coefficients, yes. And
okay, so that's what I'm saying. So if we want to analyze this, we have to calculate the coefficient, that's B0 and B1.
Yes, exactly. And this coefficients describes our line. So regression model is like a line, simple line, or plane if we are talking about multidimensional space. So we construct a model. It means that we calculate coefficients using our data set. So
okay.
Thank you for your question. Any other questions?
No.
So it's
No, I said no, sorry.
Okay. So as for your practical task, we will have a short break now, 15 minutes, and after that we will continue working on your practical task. But as I remember, last week we've had also lab works, and I want you to be sure that did you start your lab work last week or not? What about lab works, guys? Because I think that you missed.
I already finished the
I
first.
already finished the first one and I uploaded to the class, Google Class.
Great, thank you. Hassan?
Yeah, I finished the first one, but still into the second one. I haven't finished it. Do I need to, like, for each task, 1, 2, 3, 4, I have to send a report in, or a general report for all the steps?
No, for one lab work, one report. this is the rule.
one lab work, not one
Yes.
task in the lab work. So I
Ah.
have here we have I don't know how many tasks in the first lab. So
I will show you an example of the report, and
Mhm.
also you need to upload report for your practical tasks. We will have 2 practical tasks, so 2 reports for your practical. In Google Class, you also may find some example of the report, title page, some short explanation of your task, and after that, code with comments. Yes, some plots and conclusions. That's all.
okay.
Mhm.
My question was, we have 7 lab works, right?
7, yeah.
So do I have to send in 7 reports, or for each task in each lab I have to send a report? That's why.
No, not. You have only the whole lab work. It should contain several tasks, but all of them will be inside one lab work. So only lab work.
Okay. So the report I should send you is for the whole lab work, not for each task in
Yes.
lab work.
Yeah.
Okay.
Yes, the
Very
whole
much.
lab work.
Thank you very much.
Sorry, I'm quite confused. Are we sending 7 reports for the 7 lab works, or 1 report for the 7 lab work?
7 reports for 7 lab works.
Okay.
You will
So
find it here.
are we to send them? Can we be sending them gradually, or we should send 4 at once? Because it seems you said we should start with the first 4. I don't know.
You need to send first 4 labs before 15th of October.
Whoa, that's
2 weeks.
that's okay. I actually had done the first one, but it was on another system. I just recently downloaded my MATLAB, so I have to do it again. But let's see.
You have some problems with MATLAB. It's like a
Okay.
soft deadline, actually. So we may shift it a little bit sometime.
Yeah. Well, I'll try my best to be able to submit it before the end of this week. At least maybe the first 2 or first 3.
Okay. And actually, you will have defense of your lab work after uploading your report. We will discuss your report here in Zoom. Yes. So be ready to answer some questions about your code and about theory.
Okay.
So we have a break, 15 minutes. I will. You may stay here. Just I turn off my microphone, and we will continue working. Okay.
Yeah. Okay.
Benedict, can
Yeah.
you hear me? Can you please turn off your mic? I'm so sorry.
Oh, sorry.
No problem.
Let me do
Thank
that
you.
right now.
Thank you.
Okay.